So let's begin with a recap of what I talked about last time, just to give us a reminder. The idea is that we're trying to extend what we've done previously to manifolds, and in particular, we were talking a lot about the gamma operator, or the differential. So, yeah. And what we discussed last time is that this somehow detects second order properties of our L operators. I want to.
You have to rephrase what is F and what is F and G?
F and G are taken to be arbitrary smooth functions or test functions, differentiable functions. We need
some differential operator.
Yes. So the context here is that given some differential operator L,
second order.
it doesn't have to be. So this statement makes sense for any differential operator. I suppose what we should say is that if L is of order n, then F and G must be at least n times differentiable. So what this does is somehow detect the second order properties of L. So if L is first order, there's always vanishes because of if L is second order, then it captures exactly the second order properties. You can ask above this if L is n or n greater than 2, it captures the second order and other information. There's a whole theory of this. You can also iterate this.
Yes.
So this is kind of gamma of L in the sense.
Yeah. So sometimes you see that gamma L if you're working with multiple different operators. Also, if you continue with the theory, looking at rough paths, they iterate this. So you can define something like gamma n plus 1 of FG. Spend a minute to look at this, but it should just be. It should be this. We should double check this, maybe don't trust it, but you can iterate these, and in some sense, this tries to capture even higher order information, but almost all.
In easier, there is canonical projections. So you take the whole space of higher differential operators and decompose, and on each point you get symmetric product. So this is a second order symmetric product essentially. Okay, so this is not right. Really useful. Okay, go on. Thank you.
We're not going to work with these beyond the first order one. We don't really need this. But it is an essential ingredient in some generalizations. Before we continue with this operator, I want to present some examples. What are L diffusions good for? So maybe we should have a reminder of what it means to be an L diffusion. The point of an L diffusion was to somehow generalize the notion of flow associated with a first order operator. So those are all. Differential operator. L, I should probably say P here, but it's fine. And assume, say, filter probability space. Omega, we get everything right. Yeah. So we've got event state, we got concentration. So given that we have diffusion operator L and some filtered probability space on which we're working, then we say X, which we can define as being if n, which we define as x of x0, which of x. And here, yeah, t LF S X S is for any let's see. All right. So this is our definition here. We can define a stochastic process associated to the operator L and smooth functions F. This, if we insist that for any smooth function that this process is in fact a martingale, then we call X an associated L diffusion. Okay. So what I want to do then is talk about how we use L diffusion in this context. Yes, that'll be our first goal. If we give a few examples of this, and then we're going to go back and see what exactly gamma tells us about L diffusions. Well, it's fine. Actually, before we jump into the example, let's just talk about sort of the model. You're almost certainly familiar, but the Dirichlet problem. So the Dirichlet problem says, given a partial differential L, find some sort of function that needs to be just continuous and a closure of some domain, and it needs to be C2 on the interior. We need one of the case domain, of course. Given a QOL and some, well, this is essentially going to be a boundary condition. That will insist is, I think C2 is enough. C2. I'm just going to take this. Okay. And U, that is continuous on the closure, and it's C2 on the interior. So that L is 0, and that U is equal to 5. I guess I should say this, maybe it's better. Yes, we're familiar with this? Surprise here. So the idea then is that L diffusions actually give us a way to construct U. So suppose X L diffusion. I want to, in terms of this L diffusion, find a formula for U. So what do we do? So one, choose some relatively new sequence. Relatively compact domains. Such that yes, by which I mean we can actually write this a little bit nicer, such that union across n of the n. And just don't remember, relatively compact, but I mean is like the closure of the n is always properly contained. So we have this, and we find the first exit time. Tau n of x t. So that process, starting from the point x, has left. Yeah. So we talked about these before. So a first exit time is in fact a stopping time. Yes. So what we have at this point, probably it's nice to draw that. Yeah. So let's say this is D. So we have some sequence of domains, right? That converge outward somehow to the whole D. And the idea then is that if we start here, the stochastic process moves around in D1 and eventually hits the boundary. So the time when this occurs is tau 1 of x. And we can proceed by continuing, saying for this step n, when does it first hit the boundary essentially, dm. Okay. So we've assumed, of course, that x is an L diffusion. That is, satisfies this. Let's bring that. Right. Yes. Go ahead and choose test functions. Space. Test function, the UN, maybe just want to be smooth. So we're going to ask these functions are smooth and have compact support. Yeah. Yeah, I guess we could just say. And so that's if we restrict UN to DN, it's just equal to U. Yeah, DN. And we want the support that is contained in D. So we have some sequence of test functions. Then, well, we know that x is a diffusion. So what happens is then, I'll write this UN P of x, which is of course UN Steve x UN of x and from 0 to t of L UN yes, marking, all right. So what we're going to do now is stop this process with the stopping time again. Process and UN T. So as a reminder, when I put this wedge, I mean the minute of the two. Right. So what is this process going to do? Because UN and U agree on TN, this necessarily has to be 0, right? Because it satisfies the differential problem. So we get then T, UN, ln x, x, of course, equal to UN, x, x minus x is Markov. So if we take expectations of this, on the left we get 0 because that's the martingale property, and we can conclude then that UN of x I'll do a little silly thing here. So we have this, but we know that both of these, excuse me, all right, we're stopping it. We know that x t wedge tau n necessarily has to be in dn, right? And of course, by assumption, I have the axis. So really, this equality can be written for u. As again, this part right here. If we take expectations of this, well, when we take the expectation of ux, it's not stochastic. The expectation of ux is just ux. So ux expectation of u x t x. Why do you need u x? Why don't you work directly with anything to be smooth and how about this work to make sure that everything works? Yeah. Yeah, so I'm not in U isn't necessarily smooth. What I've asked for, or said to the that problem, is that it's C2 on D and just continuing on.
Oh, okay.
So these there's going to be something wrong here, not guaranteed differentiability, this sort of thing. Okay. So this all works out. Yeah, I agree. It's a little bit silly, but what can we say now? If we use dominated convergence. Again, I can make this this for all that. So using dominated convergence, we know the tau ends have to converge up to tau, the first exit time of u from D. And well, this expectation is just an integral, right? So what we get then is that ux has to be equal to the expectation of u x t wedge tau. It's unsurprising, but you should be a little bit careful. To be clear, whatever the dominated convergence, what I do is I would take the limit on the outside of this as n goes to infinity, and then dominated convergence allows me to take limit inside. So yes, great. What we've discovered is that if there is a solution to the Dirichlet problem U, and there is an L diffusion X, that necessarily the solution must satisfy this. But we haven't addressed uniqueness or existence. Okay? Basically, what we've proved is that if all of these objects exist, necessarily they're related in this manner. So let's talk about uniqueness and existence. So, whatever to assume tau is almost surely infinite. So this is 100% an assumption. It's a condition that we have to work with. But if tau is almost surely finite, and what do I mean by this? I mean that almost surely the L diffusion X will exit the domain in finite time. All right. So if we do this, then review U of X. Infinity. Future U of X. Right. So this is just writing this. We apply the limit, because the left-hand side, of course, will depend on t. We go ahead and we can interchange this limit again by down the convergence. And then what happens? Well, the minimum of t and tau is going to be tau under this assumption. So u of x now is given expected value u x tau. Right? But now what has happened? Tau is the first exit time. In other words, x tau of x is where we hit the boundary. We're solving a Dirichlet problem. We're given the values of u on the boundary. So necessarily, well, since we're taking expectations, we don't have to worry about this. This is going to be equal to the expected value 5. Right? So, why is this nice? So this is really just somehow some sort of integral condition on u. If u is a solution, then it has to be its expected value of it evaluated, as time continues. But since we're assuming now that we exit d in finite time, we can interpret the statement to tell us that actually all of the information of u is somehow told to us at the boundary. Does this make sense? Okay, cool. Yeah. So what I can say then, sure. So I guess I'll write these two conclusions. Yeah. Okay. So the idea is we have uniqueness. Yeah. This almost surely finite. Then we have to have almost surely for every x in the domain. Right? Because this is a statement about one specific x. But we're saying that no matter where we start in the domain, almost surely we exit in finite time, then u of x is simply always 5 of we can also make an existence statement. Yeah. So what we do here is if we have the first exit time approaches 0 as x approaches let's say a in the boundary. Okay. So the a here is if we take a starting point and allow it to move towards the boundary. Under that condition, in that situation, we assume that the first exit time goes to 0. If this is true, then what happens here? As we move along the boundary, tau goes to 0. X0 is literally just x. That means that we have the expected value of phi of x. Which of course is deterministic. So I will write phi a here because we've asked x to go around. Okay, so what does this tell us?
How do you show the given properties?
Forgive me.
How like u is continuous? Is it continuous?
Yeah, you take it from. I think it should go like this. So what can you say here?
It's a limit it's dominating convergence of C2 on this infinity.
Yeah. So we can say this for it. We get C2 because Q actually is satisfies an LU equals 0.
Okay.
So if you want, you can actually go ahead and file this and see that it's okay. Because we know that X is null diffusion. For continuous on the boundary, I think it basically just solves this. Because we know by assumption phi is that says that. Is that all right? Maybe not the most fulfilling justification, but I think it's hard. Trying to think what I can say a little bit better than that. Yeah, I think I'll say this. So the first statement really is it's a unique mistake. It says if you exist, it satisfies the necessary that this has to happen. But as far, I think we have to insist on the existence criteria in order to convince ourselves that you actually satisfy these properties. In which case, on the boundary, this equality. Okay. So let's go ahead and take a look at a couple of simple examples of this, but maybe somehow revealing examples. Yes.
The function phi here is not a given function for your story.
Yes, yeah. So the differential problem is specifically given the operator L and the boundary condition phi.
Okay.
Find a U that is L harmonic, L U 0, and on the boundary is equal to phi.
Yeah, sure. I was thinking the other way around. No, that makes sense.
Yeah. You can essentially say Dirichlet boundary. Dirichlet means you have the boundary given the values of the boundary. So, a couple of nice examples here. I don't know if you want all. Yeah, let's look at these as well. So, our first example is going to show us where uniqueness actually fails. Okay. So if uniqueness is going to fail, then I need to construct a situation under which we don't have a finite exit time. So kind of a nice way to do this is we're going to go ahead and say R2, R2 minus the origin. We can do this in higher dimension, but R2 is fine. And go ahead and let D be the set of points such that R1 is less than, let's keep it open, yeah, less than equal to X R2 for fixed. Okay, so I mean this is simple, right? We're looking at this. So our diffusion is taking place on here, and then our operator is just going to go ahead and be the maybe I should name this singular velocity. So 1/2 d2 d. Okay, where theta is annual. Is okay? I mean, yeah. Okay. So maybe we have some sort of intuition, right? What would happen here? Maybe we can start with the idea, what if L was first order and we had d theta? Well, the solution here is going to go directly around in circles, right? We're going to get somehow foliation by circles of the animals. Since we're at the level of second order differential operators, we're talking about diffusion, so it's going to be a stochastic process. But somehow the behavior is related, right? What this means for us is that intuitively a diffusion could start here and just go around forever. and just never exit. That's the idea. Okay. Okay. So in particular, let's go and see this. Notice if u of x solves the Dirichlet problem, which I can restate it. For the Dirichlet problem, I mean, we're given values on boundaries that would be the inner circle or the outer circle. And if we want a harmonic function for L. Okay.
It's still very different.
Yeah, yeah. So like I said, this is a confusion point. I mean, that is. Zero d u restricted to the boundary of d equals 5 or given someone given 5, right? I'm just saying.
D on L.
Yes.
It doesn't have to be elliptic. So
Doesn't what?
it doesn't have to be elliptic.
No.
And yet you have a unique solution.
No, I don't have. This is a failure.
Ah, sorry. Yes. Okay.
Yeah. I was gonna justify why this is. So like, suppose we have a solution, which I mean we should, right? Like we can write it out something like this, at least in theory. Yeah, in fact, we satisfy existence, right? We should satisfy existence. Anyway, what happens? Well, if v some function that's going to go ahead and satisfy let's say, I don't know, T2. Satisfying nu of R1 equals nu of R2 equals 0. So what I mean by this is that along both boundaries, that this function vanishes. Okay? So what happens? And u plus nu vanishes. I should be really careful. How do I write this? Yeah, let me actually do that. Now this is much better. Okay. I'm saying I have a C2 function that is radial. That is, it only depends on our radial coordinates. Okay. And moreover, it has to vanish both at the inner and outer radii. Then necessarily u of r theta plus u of r also satisfies. Do we see why? Yeah. Because the contribution to the boundary is 0, and L like the new, I say new V vanishes because it's radial. So we don't have any limits, which makes sense. So like we said, intuitively we can have solutions that wrap around forever. So there's no reason to think that it was. Okay. If you want maybe like a little bit more solid justification, what you can do is imagine unwrapping this. So you can imagine that this is really the integral R1, R2 cross S1, right? But we can identify S1 with R, something like this. Yes? Quite good. So if this happened, well, what's going on? L doesn't at all depend on the radial coordinate. So you can think that a diffusion for this can be thought of as a diffusion on R mod Z, which means that it's a Brownian motion. Is this okay? Okay. since we have this grounding motion harmony, there's no reason that it can go around. That's the whole idea. So yeah, so this shows us somehow how we can violate uniqueness. Let's take a look at another one. So we're going to be somehow using this, the existence property. So our existence property is telling us, well, we need the exit time to go to 0 as our initial point approaches the boundary, right? So let's say we have this sort of nice situation. Two existence criteria. Okay, so in this case, our setup is going to be M, it's going to be R2 again. We'll include the boundary this time. We're going to let L be less than x1 direction. Okay, so here I'm insisting horizontal. All right. And let V be sort of a silly shape. Something like this. Okay. I'm going to go ahead and label this point A. I'll be relevant. So let's think about what diffusions have to do here, right? So if we start at some point X, let's go ahead and put X on the vertical axis, although it doesn't have to be at this point. We have diffusion that only works in the x1 direction, right? So what this means is that here like this. So X is going to be X2. L diffusion. Is a ground motion. Yes, we essentially move horizontal. And what this means then is that we can only exit at 2 points. Which, you know, depending on the exact definition of our domain, who knows. So what we're going to do now is allow X to approach A vertically. This is okay? So what happens? Well, as X goes to A, under our existence results, it's necessary that U of X goes to phi of A. Yes? All right. But also, by the symmetry of the gravity motion, U of X in general has to equal the average. So phi of XL plus phi of XR over 2. Yes? So what we can say is that given this domain, if we draw a horizontal line and label this point L, and label this point R, then solutions only exist only if phi of A is equal to phi of L plus phi of R. Cute, huh? I mean, obviously a very artificial example, but it's just an interesting way to see somehow the consequences. We're only going to solve materials that probably want a domain like this. We have this sort of result. Okay. Yes. So let's talk about the heat equation, because everyone cares about the heat equation. I'm just going through all the examples in here, they're all good. How are we doing on time?
It's 5 more break.
But yeah, so when we come back, we'll talk about heat equation. Then after that, we'll go ahead and take a look at how this all relates back to the gamma operator. So in particular, we're going to see how the gamma operator tells us about the quadratic variation. Great. So we're going to go ahead and pick up with discussing the heat equation. I don't think I should call this an example of reflection because, well, what's going on? The examples and what we've been talking about so far was solving the Dirichlet equation, right? Or the Dirichlet problem. And somehow the defining property of the Dirichlet problem is that we have some domain and we're given the boundary conditions on the domain. The heat equation is not a Dirichlet problem. We should see this. Let's talk about the heat equation. So the heat equation says, given a, let's say, second order partial differential operator L, and we need, okay. And a C2 function is enough. And just continuous F CM. So I should clarify, maybe we're working on some manifold then, and we don't a priori really need any conditions like that. So yes, we have second order PDO, and we have some sort of continuous function on that. We want to think of making sense of a process in time and space. That is, we regard M as a space that evolves in time. And moreover, then F, instead of giving us a boundary condition, it tells us our initial condition of time 0. So we want to find U that should go ahead and be, what to say, U plus N. LU plus the root entity U equals 0. And U of 0 x equals x. So please see that this is somehow not the same problem. It's the difference between boundary conditions versus initial conditions. Okay, so we're going to start with the same point. Suppose that x is an L diffusion. Right, and I mean, a priori, we don't have an existence or uniqueness result of this. We don't really need uniqueness, but we do need at least existence. So anyways, we're assuming that this exists. Then what happens? Then the process T xt x is L hat, which is defined as being L plus T. Can we see this? I mean, this boils down to the fact that necessarily in time directions, it's a first order operator. So taking through this process in the time direction. So we're working just fine. You can also put it directly in here. This is okay? All right. So even though we really only have a PDO in space, we can somehow bring this to become a diffusion for this space operator, if you want to call it this. So what does this mean? I can rewrite the formula that we've been using multiple times now, right? This means that for any appropriate test function f, that okay, so we're changing notations here. That's fine. So for any appropriate test function, we're gonna switch to phi now. That necessarily n phi t as defined before is for any function I, we can name of it, and it's just two n I t x. Yes. But no, I have to be careful now. So our statement, but L diffusions, L hat diffusions, isn't quite tell us this. It gives us that it's a local martingale. So this wasn't a problem in the previous setting because we insisted on unbounded domains. But this is no longer the condition, right? Like, even if M is a compact manifold or something like this, zero infinity is not. Should we review what we mean by local martingale as opposed to martingale? Or do we? Anyone doesn't remember. The short version is that local martingale means that there's some sequence of stopping times that diverge. And for each stopping time, this is a martingale stopping process. Simple. Okay. So let's go ahead and write this equivalently. And this is just sort of an exercise in writing things differently. This is written at the integral level, right? Where we've got some interval making sense of this. But we can write equivalently d phi t x is minus hat I. Yeah, I know that it is. Yeah, maybe it's nice to write this like this. T x equal to 0 m. So what we have here is that it is equals m is quality modulo local martingales. Right? So what I'm saying here is that if you wrote this expression out, we know that this whole thing is a local martingale. Raising it up, the statement there up to the level of differentials, this will replace phi txt minus phi 0 x 0, right? This will replace the integral statement. And then this isn't an equality, but it's equality up to something that necessarily vanishes for unstopped as a stopped process. Okay. So what are we going to do with this? Well, we're going to go ahead and make an assumption, right? Because this is about as far as we can go without some sort of hypothesis. What to do then? I want to insist that process does not go to infinity in finite time. That is, we don't have some sort of explosion. So I define tau. Yeah, okay. So yeah, it's like x e equal e 0. That's x. And just to make clear what I'm saying here, because this is sort of an awkward statement. What I'm trying to insist is that this can't be infinitely far away in finite time. Okay, so this is when it essentially is infinitely far away. And insist, assume that x is equal to yeah. That is, stays in M forever. Almost surely. I tried this out. I see.
The statement becomes, I mean,
Obviously, this is equivalent to what we're talking about in the sense of the Dirichlet problem, but when it hits the boundary somehow. But in that sense, it's very easy to make sense of whether we have a clear boundary of our domain. Here's a little awkward. So what I could say to write it in level of probability is that the probability that x is in M for all t. Zero, whatever is this is the interpretation. There's no explosion. If this bothers you, like the easy example to think of, I mean, going back to standard first order differential operators. Just think of the example where we say that we have a function that its derivative is 1 over a minus t. The time n explodes to infinity, it is no longer in the manifold being R. So then we're avoiding this. We're saying that our process has to stay in the manifold forever. So then what happens? Suppose moreover, that U is a bounded solution.
This assumption, if you have a compact manifold, it doesn't.
Yeah, if you have a compact manifold, there's no problem.
Okay.
Okay, you don't need to worry about any of this.
Sure.
It's a very good point. Which is why it's a reason why
I wouldn't think about making such an assumption because I always assume.
Yeah.
Yeah.
Yeah, no, I agree. Okay, so we're also going to assume that U is a bounded solution. Okay? That is that its value doesn't explode to infinity or anywhere manifold for time. So then what happens? Well, we have this equality up to over scales. So let's go ahead and fix some n time. And then put that on 0 t plus m. All right. So since U is a solution of the heat equation, it's on R plus cross m. Of course, it's also a solution on 0 t cross m. So then what's going to happen here is that we can go ahead and say U of t minus s x minus U of xs or t minus rho s. Yeah, yes. Well, that. Yeah. U and we're going to t minus r. X d r. Right. So we have this process. So we essentially have a process that is ending time t. For 0 is less than s. It is a low particle. In s, so it's not zero. So we're thinking of this as a family of stochastic processes in x by s. We're flipping it. Sorry. Okay. So then, in other words, what we're going to say is that if we consider expectations, well, this has to have expectation 0 for some sequence of stopping times s in here. But now, when we think about this, we've insisted that U solve the heat equation on here. So this is actually 0, right? So then what can we go ahead and say? So U of t minus s xs of x minus U of tx equals 0 modulo particles.
I mean, And I keep on seeing these equations that go backward, but I don't really know why we need them.
Well, I'm gonna go ahead and show you this. The key is that we're gonna want S to move up towards T.
But why don't we just write U S if conditionally U goes to X instead?
There, that's why I'm gonna do this. Okay, so the reason is that we're going to want to relate U of T to U of 0. Okay. So if we ran it the other way, if we had S, or if we had 0 and then S or something like this, we would have to run S up to T.
Yeah.
And no, we're going to do that. So it's going to be a justification for this.
Well, so this is like a way to do that. I just don't know why we do that.
But there is a justification in here. It has to do with, I think what would happen if you had U of S xs minus U of S x. Yeah, that's correct. Yeah. I need to write it out. Something funny happens where yeah, I'm not seeing it exactly. Something funny happens. We can write it out if you want.
We can also talk about
That's 0. No, x minus U of S 0 to minus 0 to S. So out of U, this should vanish, right? Yeah, this will vanish. So what happens here? If I let S, what am I doing? Why is this? Oh, 0 x. So if I let this go up to T, it's not immediately obvious to me why I can do this. I mean, we know this is going to be, or this will be 0, the L hat here, because we're solving
it. Probably is a reason why we do that.
Oh, I think what we want to be worried about is, how do we see this? Yeah. Okay, I think here's the issue. We have U0 x, right?
X, yeah.
But at 0, we know we have f of x, but we don't necessarily have this. So we don't have that the heat equation satisfies 0 necessarily. So I'm funny happens here. I'll think of it. I'll get you a better answer. There's something funny. And this is really important. Yeah.
Nah. I was going to the backward formal operation, and you always see it written backward.
Yeah.
But
I know. I've always done this as well. So it's
I think it's because we use some kind of argument from ideal systems when it comes to the characteristics. But I'm not so sure. I was just asking. It's fine. Go on.
yeah, no, this really bothers me. Why don't we do that? Okay, yeah, I guess we'll just leave it for a moment. But yeah, that really bothers me a lot, and I'm thinking about it. Anyways, we have this, right? But what's going to happen here? We have assumed, this is our second assumption, that U is bounded. So of course we know that this is bounded, which means that the local martingale over here is bounded. And if it's a bounded local martingale, then it's just a martingale. Does this make sense? Anyways, I'm not going to do that. Let that question be. Okay, so in other words, since this is properly an actual martingale, this means when we take expectations, we actually have to get 0. So in other words, let's say it is a actually. Since we go ahead and consider the limit as s goes to t. And here we're going to go ahead and get u of 0 x t x. Yes. Sorry, I don't know what's happening here. This is very strange. Anyways, all right, so here, this is not stochastic. We're taking expectation equals whole thing. It's not stochastic. So this u of t x necessarily has to be the well, we already have this expectations u of t x x, right? This is literally just taking expectation where this actually has an expectation 0 in this previous statement. We can go ahead and take the limit because everything is bounded and we've got down convergence. So we can say that this goes up as s equals 0 of u 0 x, right? And then what does this tell us? Right. But then if we actually consider this at time 0, we have the initial condition, right? So this is by the initial condition f of x, t, x. Yeah, about this running backwards, this is where something's going to happen.
Yeah, I think so.
Just I have to write it out so I have to see it. Something doesn't land.
I'm looking right here.
It's the bounded convergence. It's the dominated convergence.
Yeah.
We don't have. Okay. Yeah. Okay. I'm good. I'm glad we solved this. Yes. If we ran this forwards, so if we let this to be s 0x like this. If we ran it forwards, yes, then we won't have dominated convergence. Yes. Okay, anyways, so we have this nice convergence, and we insisted, I mean, between again dominated convergence and the fact that E is bounded, this actually has to be equality. So we can say that we actually have a solution to the equation. So assuming that's almost really infinite. That is, we don't leave the manifold. Of bounded solutions. U of x is necessarily equal to the expected value of the initial time, the initial condition. Evaluated at the flow. Yes? Cool. And again, this reflects what happened last time, that what we were given was the boundary values, and we saw that evaluating an L diffusion on the boundary and taking expected value actually gives us the value of the function we want. I should be careful, right? I should have read u of tx. Now what we're seeing is that at time t, we ask ourselves, where has an L diffusion gone if it started at x? At that point, figure out the initial value and then take the expectation of this. Yes, does this make sense? So there's a nice way you can see this equivalently, is that consider all paths starting at x then travel for time t. Figure out what the initial value is at the end point of all these patterns and take the average of that. Great. So let's go ahead and move on and talk about the gamma operator and how this relates back. Initial. We're going to do it again. We've already seen this. We know what the conditional is. It's an operator. It takes two smooth functions and somehow computes the second order behavior of so we can say so. Make following observations. First, and somehow fundamental. This L can be written as the sum from j of aij dif g plus the sum across I of vi di. Yeah, I think that. So if we can write this, that is, L is second order. L has no constant, right? Then differential specifically detects the second order fact. That is, I don't think I need 1/2 now. But it's again the sum of ij, aij, di. And I should say all of this in local coordinates. So, there's nothing to be done here, but yeah, we're working in manifolds, so I'm saying within some local coordinates, we have this expression, and the conditional specifically detects the second order component. Okay, this is clear. I think I'm clear here. Also, let's say we have number 2. This L is actually a Laplacian. Then, yeah, let's go ahead and say R. Then the conditional. So sometimes we'll write this, by which I mean we're considering it as a quadratic form. It actually goes ahead and affects the gradient. Magnitude of the gradient of the function. Yes. This is just sort of a reiteration. So often what we'll do is, we won't insist that we can write this in coordinates, but instead we have, we can just write it as local operators, or we'll have a first order and then some collection of second order. That is, so vector fields. And L is 0. So remember, interpreting AI squared to be the composition of the vector fields, and our motivating discussion of why we construct L diffusions was the fact that for iterated vector fields like this, it's never actually a vector field, right? AI squared itself. It's an operator, but it's not a vector field. Well, in this case, the conditional is exactly what we would expect from this local coordinate system. That is just some I of AIF. Yes. I mean, this follow. I mean, you can see this is following sort of immediately from number 1. Then what happens? Okay, and we can say something about vanishing, like Shop only vanishes if all of the vector fields vanish. Do I want to go semi martingales? Yeah, I do. I need to. I don't think we defined these yet. You defined semi martingales. What? Have you defined semi martingales?
I said it quickly, very quickly.
Yes, we have some process that we will call xt. X0 plus mt plus et for mt martingale. And et is an adaptive process, locally finite variation. I'll say adaptive. That we call semi-martingale. Yes. So where does this come from? What was the motivation for this? Okay, so x0 really just gives us some sort of starting point. MT corresponds to exactly what we've been doing. We want L diffusions to be martingales. We have to introduce AT, so a process of finite variation, because our operators can also have a first order component. And the flow associated to a first order component is a adaptive finite variation process. This is okay? All right, so then what happens? What we're going to be able to say, and this is okay. So then, I think it's coming. I'm not going to write it down. So on manifolds, we always have this problem that we could blow up. I mean, we've talked about this a few times. A priori, these definitions, semi-martingales, etc., don't put anything about this, but I'm going to go ahead and assume there is some stopping time. And I will insist that all of my processes are stopped at the stopping time such that we don't actually leave, okay? So all of my processes, we probably won't stay within the manifold, even if that means they have to be stopped at some point. Okay, so now, attention, assume, or let xt be a semi-martingale such that it's effectively a L fusion. So such that LFC of x, which we define essentially in the usual way, minus 0 minus 0 to t of L x. And it should all be an x, right? So it's 0 x equals x anyway. The S is a local martingale. And then we have to worry about local martingales because, again, we're on a manifold that we don't really trust these things behave. I guess I can make this non-continuous. Continuous local martingale, and we're also going to insist that NFT and XT have the same lifetime. That is, that the stopping time I was just mentioning for the two of them are the same. Then the quadratic variation. Satisfies that so we talked about this at some length early on. So quadratic variation itself process, right? Or maybe I shouldn't write. Now, get rid of these t's. So given some process x, f of x, g of x are again processes. Their quadratic variation is again a process. This d means we're acting at the level of differentials. Oh, maybe unsurprisingly, this is the same as the quadratic variation for these two processes, but this is the one that we really care about. The Karevishan protects this as well. Yes. So, I can say this as well. So we're going to only have equality here if the process is a bounded variation. This is all right. We can do a proof sketch. How many do I have? I always have 10 minutes. Okay, yeah. Let's go for a proof sketch, and then I'll make a couple of other statements that I'll probably provide with that proof. So the proof sketch boils down to, surprise, surprise, the Stochastic formula. So what we're going to go ahead and do is f the speed function of the manifold, and phi is essentially going to be smooth function. We're going to pre-compose these so that we can actually apply Ito's formula. So what do I mean by that? We don't really have an Ito's formula on manifolds, but of course we have an Ito's formula on Rn. But in this case, we just okay, fine. We don't put it on. We would be in trouble right now. So what we're going to do now is write out the stochastic process that associates with this on the level of differentials and apply Ito's formula. So we know xt is not semi-martingale that satisfies this, right? So we can actually write that d of phi composed with f d is I'll draw t. This is okay. I mean, this is just this is really the assumption on x. So we have insisted that it's that nft is continuous local martingale. This is exactly what we said. So the Ito's formula. And again, I said this, but I really want to stress, we don't have an Ito's formula for f, but we do have an Ito's formula for phi applied to f. This is the level at which we have to understand this. Then what we actually have is that d phi of f, I'm going to remember this, so we're going to have to try, is equal to sum across I to n of di phi. So here I'm denoting partial differentials by df applied to f of x. Where, of course, fi means the ith component of f plus 1/2. So this would be our typical table rule. This is the Ito correction term. J component n, di j applied to phi f of x and quadratic variation. Yes, we're okay with this. This is just E as well. Ignoring the fact that X is a stochastic process on a manifold, F of X to be regarded as a stochastic process on Rn. So now, what happens? So we're going to go ahead and equate the drift parts. So by drift parts, what I mean is the part that follows out as a process of activation, or equivalently this first order part. So what this following this, we're going to go ahead and see. Oh yeah, I do need intermediate stuff. So ignore it. So we have this, but we're working with a diffusion operator L, right? So what we want to go ahead and do is replace this with L at I. And yeah, we can get away with that. Oh, and also I need a PT here. There we go. Sorry, this is a little differential, so I need this. So we can write this, right? Because and this is what it means for X to be a diffusion of X. There. So now we have this. Well, if we go ahead and equate the diffusion parts of this. So I'm going to go ahead and do the same trick with this. Sorry, I should write it more clearly, but this is L of 5F. Yes. Right. So what do we get? I'm going to go ahead and subtract the L of X term to the first order terms from the right side. And we have L of phi of F minus some plus I di phi of F I. This right with my X. Yeah. Sorry, I'm being a little skippy here. So we're trying to do these local differentials. This has to, of course, equal what's not on the right side. So we're going to have 1/2 or something of I j phi. Yes. So, this is as far as we can go in the abstract. But what we'll go ahead and do now is take a specific example. So we're going to take n equal 2. So we're just going to up 2 right now. And let's say phi of x, y would equal x times y. This is all phi, right? Like the dimension we're free to choose, and we just need phi to be a smooth function on R2, which of course x times y is. Then we apply this here. We're going to have L of F1 times F2, right? That's literally what we mean. So we take phi of F, take it components, has to equal, okay, right here, let's think about what each of these does. If we take the D1 phi, we get y, right? And if we take D2 phi, we're gonna get x. I guess let's make this a little cleaner like this. Yeah, x1, x2. I don't know if that makes it nicer or not. Yeah, I can write this di phi, then x I plus 1, yay. I think it's better. But I check for I. We don't take derivatives, but whatever. So we write this, we're going to have the sum of both of these. So when we apply this to LFI, this will be xj. So in other words, we have f1 LF2 minus f2 LF1. That's really all that's happening here. And of course, all of this is evaluated at XT. Now let's evaluate the right-hand side. So if we take phi and take two derivatives of it, if they're the same derivative, di just vanishes. If they're the opposite derivatives, we're going to have one, right? So we're going to have one as the quadratic variation of the terms that don't match. So, and we have two of these, right? We're going to have d1, d2, and then separately we're going to have d2, d1, which is why 1/2 goes away. And we wind up with d f1 of x. Yeah. What do I do? Sorry. All right, so this is the level of differentials. In particular, of course, you'll notice that this really is the kind of type. But yeah, that's all I really want to say. So I'll change it F1 and F2 to G equals jump twice the jump. As we wanted. Go. The two comes from the vector that calculated chunks that it's in 1/2. Some reason I thought we had to pass to no, that's first time. Cool. So what we have here, and this is more than as good as the actual proof, is that calculated chunk really does represent quadratic variation. So there's a direct connection. I mean, we knew just intuitively, or like thinking about this, yeah, in the answer, right, that the quadratic chunk should capture the second order behavior of L. But from our former theory of SDEs, we understand that the second order behavior of an operator is exactly what induces the fact that we need a stochastic process. That a locally bounded, a bounded variation process isn't sufficient to obtain some sort of flow. And this again reinforces the duality. I will go ahead and write out a few more statements that will be useful in the sequel. I think the next time I talk about it, we'll have enough time to prove these and see some information about them. So the following are equivalent. Let's say, yeah. For R linear map, it takes smooth functions on M. Yeah, smooth functions on M. So of course, what do I want? I want L to be second order PDO or generally a partial differential operator. All of the equivalents. First statement is that it is exactly that. L is a second order PDO. Is L like 0? I'm not writing L1 equals 0, but just in case it's not comparable, all I mean is that there's no first order component. And then secondly, that we got to shop. No, it's like this. We have a second order chain rule. L satisfies the second order. L by F necessarily has to be so I for whatever dimension we're in F. This is composition, not multiplication. P by F applied to L by W. Plus J Ti J I F applied to kind of jump. Yes? Okay. So what's going on here? Well, I mean, this first term here really is just regular chain rule. There's nothing surprising there, right? The second order one, we know a priori, that we should have a second order rule like this, but we would expect the quadratic variation to show up here. So this statement, one direction of it really just follows from this. The fact that we know the quadratic variation and the coefficient are directly related. You have to be a little bit careful about making sure you write this out properly in local coordinates. Sure, I should say if you want. So, C2, don't really need, or C infinity, are really and cases or something. Okay, this is just another way of seeing that the coefficient captures second order behavior. Variation. So let me give one other statement and we stop. Or do you people need to go? That's fine. The only other statement I was going to give is that if we do this whole construction, the coefficient and the second and the quadratic variation will be 0 if and only if L is first order. And equivalently, we compounded variations. So we know it goes one way, right? We know that if we have second order behavior, we have to work with stochastic processes. It says it the other way. If we have the coefficient vanishing, then necessarily we're actually working with the stochastic processes. All right, leave it with that. Thank you very much.